Now that we've introduced our rule for derivatives of exponential functions, I'd like to combine them with several of our other rules that we have for differentiation. So first up, I would like to differentiate f of x is equal to x squared times e to the negative 2x power. Now we are going to proceed with the product rule. However, in an alternate universe, you could also use a rule for exponents and express this as x squared divided by e to the 2x power, and then apply the quotient rule. That's not what we're going to do today, but just wanted to let you know it is a possibility. So f prime of x, we're going to treat this using the product rule. So first, times derivative of the second, plus the second, times the derivative of the first. Now, product rule doesn't finish the derivative for us, but it does give us a couple more basic derivatives to work with. Now, for this expression, e to the negative 2x power, this will be a situation where the chain rule is needed because it's not simply e to the x, it's e raised to a power other than x. So with that in mind, derivative of the natural exponential is the same natural exponential. Then the chain rule says multiply by the derivative of whatever the input to the exponential was. Then we'll have a slightly easier time over here with a simple power rule. Now, this derivative is now ready for us to complete. Derivative of negative 2x with respect to x will be negative 2. This will be plus 2x e to the negative 2x. Now, I do notice that there are some greatest common factors that could be pulled out here. I think I am going to pull out a common factor of negative 2x e to the negative 2x. So from the first term, I've pulled out the negative 2, I've pulled out the e to the negative 2x, and I've pulled out one of the x's. That'll leave us with simply x. Over here, I've pulled out a 2 and an x and an e to the negative 2x as well as a negative. Well, I've pulled out all the factors there, so we'll be left with simply a 1. Now again, it's not 100% necessary for you to factor these at this point. However, in future chapters, after we differentiate, we're going to be doing more stuff with them, so it's beneficial to put them in a factored form. Now for part B, we actually have a couple different options here. We have y equals 2 to the x times 1 plus 5 to the x power. I'm going to demonstrate how to do this two different ways. And the first way that I'd like to do is making use of the product rule, since we do have a product of two things. So product rule states this will be the first function times the derivative of the second function plus the second function times the derivative of the first function. Now do keep in mind that for exponentials other than base e, the derivative is going to involve multiplying by the natural log of whatever the base of the exponential is. So this will be 2 to the x times derivative of 1 is 0. Derivative of 5 to the x would be 5 to the x times the natural log of 5. Then we'll have our 1 plus 5 to the x power times this derivative. Derivative of 2 to the x would be 2 to the x times the natural log of 2. Now anything that you do with this algebraically afterward, that's completely up to you. You could apply the distributive property or things along those lines. However, doing this one alternatively, we could also take the 2 to the x and distribute it to the two terms that are inside here. So 2 to the x plus 2 to the x times 5 to the x. Now when you have the same exponent and bases like that, you can actually sort of factor out that to the x power and call this 2 to the x power plus 10 to the x power. This derivative does not involve the product rule because there are no more products, there are only exponentials. So dy over dx would be the derivative of 2 to the x, which is 2 to the x times the natural log of 2, and 10 to the x, which would be 10 to the x times the natural log of 10. And I assure you, algebraically speaking, this statement is equivalent to the statement that we got using the other color of ink. A couple more examples on the back of the page. Part C, let's throw some trigonometry in here as well. We have g of t is equal to 4 to the t power times the sine of 3 raised to the t power. Now we're going to start with the fact that this is a product and apply the product rule. So g prime of t is equal to the first function, 4 to the t, times the derivative of. Please notice that for this derivative of, we're using d over dt rather than d over dx due to the fact that our independent variable is now t. Same thing goes for my second expression over here. When we do second times the derivative of the first, that'll be sine of 3 to the t power times the derivative with respect to t of 4 to the t power. Now over here we simply have the derivative of an exponential whose base is not e. Over here we have a chain rule because we have the sine of 3 raised to the t power. So that chain rule says start with the derivative of the sine function, that'll be the cosine function. Then multiply by the derivative of the inside function. So multiply by the derivative of 3 to the t power. Then our other derivative here at the end will be 4 to the t power times the natural log of 4. So one more derivative to take right here. This is 4 to the t power times the cosine of 3 to the t power times 3 to the t power times the natural log of 3. Then, well, there isn't really a great order to put these in, is there? We'll just leave it as is for now. Now, as far as simplifying this expression is concerned, these are definitely not like terms. Really, the only thing that you could do is something like what we did with example B, and take 4 to the t power and 3 to the t power and combine them into 12 to the t power. But outside of that, the calculus is done. The algebra is up to you. Last example problem that we're going to take a look at is going to be h of x is equal to the tangent of 5 raised to the square root of x power. This one is multiple layers of the chain rule since we have a function inside of a function inside of another function. Sort of like when you're dreaming and then you start sleeping in the dream and you dream in the dream of your dream. Oh my goodness. So we'll start with the derivative of the outermost function. The outermost function is the tangent function. So that'll be the secant squared of the input. Then the chain rule says multiply by the derivative. We're back to d over dx since our independent variable is once more x. And we're differentiating 5 raised to the square root of x power. Now at this layer, our outermost function is 5 raised to the power of, so we're differentiating an exponential. To differentiate this exponential, that'll be 5 raised to the same power times the natural log of 5. Then the chain rule says multiply by the derivative of whatever the input was. The input was the square root of x. However, in anticipation of the derivative, anytime we talk about a square root, we're generally going to call that x raised to the 1/2 power. That is simply going to be a use of the power rule. That'll be equal to 1/2 times x raised to the negative 1/2 power. So there's really not a whole lot that you can do to make this more aesthetically pleasing for everybody. But what you could do is take that negative 1/2 power and the 1/2 and toss those into the denominator as a 2 square roots of x and throw everything else into the numerator. Again, that's not going to do a whole lot to make this more aesthetically pleasing, but, you know, what the heck. Math isn't always as pretty as I am.